nanohub.org.
Now we're going to be talking about scanning controllers in dynamic atomic force microscopy, in particular in tapping mode AFM. So far, we have really talked about what happens when the oscillating probe approaches the sample, interacts with the sample. Now what we want to do is to scan this oscillating probe over the sample. We want to understand how to adjust the feedback control parameters that require the amplitude to remain constant, and so on. So that's what we're going to focus on today. This is a very relatively short part of the discussion because we can get into pretty much a lot of detail regarding controls theory, but it's a bit out of the scope of this. Also because it turns out it's not a simple dynamical system to do controls on, because it's very nonlinear and it's very non-intuitive in some ways. So we'll just discuss the basic ideas and proceed from there, okay? Okay. Now, the first thing to keep in mind is that when you do a tuning curve and you choose the drive frequency and resonance, you have a free amplitude A0, as shown here. And then you approach the sample. Hopefully, if you do an amplitude versus Z curve, you see the amplitude decreasing, you see the phase changing as you approach. And then you choose a certain amplitude as your set point, let's say A. A is usually less than A0. And then you scan over the sample, and what you're trying to do is try to keep the amplitude constant, and you do so by changing Z. All right? So, for example, let's say you're oscillating steady-state amplitude A on the left as you're scanning towards the right over this bump. As soon as you hit this bump, what's going to happen to the amplitude? The amplitude is going to want to decrease, right? Because there's less room to vibrate. And so the sensing system then tells the controller that your vibration amplitude has gone down below the desired amplitude A, and therefore the Z needs to be moved up. And so the Z moves up, as shown by the red line, in order to keep the amplitude constant. And you scan over the samples in the following manner. Okay? There are two important questions that come in here. How does the system sense the amplitude? A. Because after all, it's a vibrating cantilever, right? It's a time-dependent motion. What is it that tells the controller the amplitude and phase of this motion is this much? And that's what is a lock-in amplifier. So we'll talk a little bit about a lock-in amplifier that all AFMs that work in the dynamic mode must have. And then the question is, the Z controller is really doing some sort of feedback on the amplitude, which is the output of the lock-in amplifier, okay? So we're going to talk a little bit about how the Z controllers work in tapping mode, and then about how to optimize it for good performance, and so on. So there is something called the error map, as most of you who have done AFM are aware of. The error map is basically the difference between the actual amplitude A and the desired set point amplitude ASP. Okay? So if everything is nice, in effect, the error signal should be 0. You want the amplitude to be constant throughout the image. Okay? And the controller tries to make that so. How it does so is a typical controller law that's used is what's shown on the bottom right. The Z piezo is moved in a combination of two effects that are proportional that depend on the error signal. So the first term requires the Z to move proportional to the error signal. So in other words, what ends up happening is that if there's a non-zero error signal, the Z piezo moves in the opposite direction effectively to bring it back, change the Z so that the error goes to 0. Okay? This is called the proportional gain, Kp. There's an integral gain, K sub I, associated with it. K sub I, what it does is it tries to not only react or move the Z proportional to the current error signal, but it also looks a little bit at the history of the error signal. It integrates not only the error signal now, but in the last millisecond or microsecond or whatever, how much was the error signal, accumulated error signal, and in response to that also. There's a reason why you want to include the integral controller here as well. Okay. Now, I want to quickly emphasize one thing, that if you've adjusted these parameters correctly, if you've adjusted the proportional and integral gain correctly in your system, in principle, the amplitude should be nearly constant throughout the sample, except where you have these edges, where you have an edge, you hit it, and there's some distortion because it takes a little while for the controller to get back to the same amplitude, right? So if you plot the amplitude over a scan, it ought to be basically constant. Ideally, in fact, it should be flat, because you're controlling the amplitude should be constant. So you should not see any features in the amplitude map or in the error map, ideally. Now, you won't believe this, but there are a lot of people who do not adjust the proportional and integral gain parameters properly and present the error map or the amplitude as the image. Because, so if you don't understand the basic mechanism of what's going on, all you look at are images, right? Then you can get confused, because what can happen is, for instance, let's say you scan over this sample, you hit that object, the amplitude suddenly changes, so you have an error. As soon as the amplitude changes from set point, you have an error. The controller is not well adjusted, so after hitting the edge, it has to keep going a little bit further before it moves the Z to a position where the amplitude is the right one. If that's the case, then if you look at the image of the amplitude of the signal itself, you will see these edges of every feature, right? Because everywhere else the amplitude is constant, except when you hit edges, there's a little transient area where the amplitude is not constant anymore. And so if you look at the error map or the amplitude map, you always see edges of the objects. You don't see the real height of the objects. You just see edges, right? Because it should be perfectly constant if you have the correct feedback control parameters. But nonetheless, people see just the edges of objects and think it's the object itself. And I've actually seen even papers where people plot the error map and just say it's the image of the sample, which is a problem, as you can see, right? In fact, error map should be used to tell you, if you see the object that you're imaging in the error map, it actually means you're doing the imaging incorrectly. You don't have your imaging parameters set properly. Okay? It's a very important thing. Okay. So let's talk a little bit about how does a lock-in amplifier works, because these days in most AFM systems you actually are able to adjust some of the parameters of the lock-in amplifiers itself. So the lock-in amplifier is what is taking the output of the photodiode and converting it into an amplitude and a phase, and the controller, Z piezo controller, is acting on the output of the lock-in amplifier. Okay, so let's take a look at how the lock-in amplifier works. Your dynamic board in your AFM generates a signal cosine omega t. All right, this omega is the drive frequency. So when you do a tuning and you choose a frequency, that's the omega. Okay, it generates, let's say, cosine omega t and a sine omega t. Well, what you do is you take the cosine omega t and feed it to the cantilever forcing to the dither gears and shake it. As we discussed, as the cantilever bends and interacts with the sample, the reflected laser spot is bouncing up and down in the photodiode, right? Keep in mind that while you're shaking the cantilever with cosine omega t, its vibration response is, we expect it to be cosine omega t minus phi. Remember? That's what we did. We said that in the simple analysis, we allow the response to be simply another amplitude with a certain phase lag, correct? It should be just a cosine omega t minus phi. But in reality, there are other things that creep in also. Certainly noise creeps in. There's noise in the output of the photodiode, right? Why is there noise? The noise comes from many sources. You have thermal noise, you have laser shot noise. It's a sensor. There's always a background noise in a sensor. So that all feeds in to the output of the sensor as well. Okay? You also get a zero. You also get a non-zero component. Why is that? Because you may not have perfectly centered the reflected spot in the photodiode to 0 exactly. Maybe off a little bit. If it's off a little bit, there's a non-zero voltage, DC voltage, coming out of the photodiode. I mean, in order to get a 0 DC voltage, the spot needs to be dead center, right, of the photodiode, equal intensity on both halves, right? Well, that doesn't happen. In fact, you may center it, but during an image it may drift a little bit, and you have a non-zero amplitude, a non-zero DC shift. So you also have an A0 part. So in addition to what theoretically we expect, just A cosine omega t minus phi, you also have a DC term A0. You also have noise. But it turns out you also get certain higher harmonics, right? These harmonics happen due to all sorts of nonlinearities in the system. They can happen, for example, due to the photodiode output being nonlinear as a function of motion of the laser spot. Okay? It can also happen due to tip sample interactions that generate higher harmonics. There are many things. These are very small perturbations. Now you must understand that most of the signal that I've got there is dominated by A cosine omega t minus phi. The rest are all small perturbations, noise is small, harmonics are small, and so on, okay? But nonetheless, that's what you get out of the photodiode. Now, I have put in some signal conditioning because you never take, the raw output of the photodiode is very, very difficult to access. There's always some sort of a signal conditioning box. Either you need a amplifier, because it's a very small signal, you need to amplify it a little bit, and you typically need an anti-aliasing filter, which filters out really high frequency noise in it. So those two are the basic components of some sort of signal conditioning has to happen before you actually acquire the data. And most AFM systems allow you to plot the output of the photodiode. If you find out the right channel, you can actually get the waveform of the tip oscillating. Most AFM systems allow you to do that if you've got a nice oscilloscope that you can tap into, and if you're patient enough in sending emails to tech support for your AFM system and telling them, look, I need to access this signal, and they'll say, oh, there is this little BNC channel output in the back. If you do this, and then you can access this signal, okay? You can access that signal, the signal that's before going to the lock-in amplifier. So this is what's coming out of the photodiode. And remember, when you do tapping mode control, you're trying to do feedback on the amplitude A. You want to keep A constant, even though the output of the photodiode contains A0, A2, noise, etc. All you're doing feedback on is A. The question is, how do you extract A from the signal output of the photodiode as you're scanning the sample? So that's where the lock-in amplifier comes in. What the lock-in amplifier does is the following. The same signal cosine omega t that's exciting the cantilever, the same signal is taken and multiplied with the output of the photodiode, with the conditioned output of the photodiode, okay? So if you multiply cosine omega t with this signal out here, you will notice two things happen, okay? So the intent is you multiply the signal and you integrate it over time, okay? That's the intent, right? So let's see what the intent is, and we'll see how it's actually accomplished. So the intent is to multiply cosine omega t with this entire output of the photodiode and integrate it over time. If you multiply cosine omega t with this term, you're going to get terms like A0 cosine omega t, right? That's the first term. A0 cosine omega t integrated over time is going to give you 0, because it's a cosine wave. You do it over certain time periods, it becomes 0. However, if you take cosine omega t multiplied with the second term, you get A cosine omega t minus phi times cosine omega t. That, it turns out, actually has a non-zero part, because cosine omega t minus phi can be written as cosine omega t cosine phi minus sine omega t sine phi. So you have a term cosine omega t times cosine phi, and then you're multiplying the whole thing by cosine omega t, so you get a cosine squared omega t, which then has a non-zero average, okay? That's the idea. So the idea is if you multiplied this whole thing by cosine omega t, you would automatically be picking out the magnitude of only the term that has cosine omega t in it. Not the DC term, not A0, not A2, nothing. So it uses the fact that whenever you have a sine series, you multiply with cosine omega t. The only non-zero term that remains is the one which is at the same frequency as the reference signal of the lock-in amplifier. So the reference signal is cosine omega t, and when you multiply it with this signal and integrate it through, the only non-zero term that remains is the Fourier coefficient of the term, which is at omega. That's all in the signal. That's the idea. How is it actually implemented? I mean, how do you do integration in an analog circuit, basically? How that happens is, when you multiply the signal, you simply pass it through a low-pass filter. So remember, if I multiply cosine omega t with that entire signal, I'm going to get some terms, DC terms, I'm going to get some terms at omega, I'm going to get some terms at 2 omega, I'm going to get some terms at 3 omega in the frequency component of the signal. All I'm trying to do is to get the zeroth harmonic, or the DC component of that signal. The DC component of the product is, in fact, the amplitude A, effectively. That's what I'm trying to say, okay? So all you do is, you have to take this product signal and pass it through a low-pass filter. So this is, in Fourier domain, if you're familiar with Fourier domain, the representation of a filter, okay? So imagine a filter as being a box where, depending on the frequency content of the signal coming in, you either attenuate the signal and make it zero, or keep it at a given value, right? So what ends up happening is that there is up to a certain cutoff frequency, FC0, it allows all frequencies to pass through. Beyond that, it attenuates the signal completely, okay? So as a result, when you take this product signal, pass it through a low-pass filter, what you end up getting is basically the term that multiplies cosine omega t in the signal. So let's go over this again. I've got that term on the top, that's the output of the photodiode. I'm multiplying it by cosine omega t, and we're asking the question, you have many product terms, right? Cosine omega t with the first, second, third term. And they occur at different frequencies. The only term that occurs in the DC, in the product signal, is going to be the term involving cosine omega t in there, right? So I'm going to write a cosine omega t minus phi as cosine omega t cosine phi minus sine omega t sine phi, multiply the whole thing by cosine omega t. So I'm basically going to be left with a term that is a cosine phi, effectively, maybe divided by 2. It's not so important, okay? So when I do a low-pass filter of this signal, I get effectively a cosine phi, okay? Which, if you think about it, is the coefficient of the term cosine omega t. So what multiplies cosine omega t in the signal up there is really a cosine phi. That's what comes out here. In the same sense, the lock-in amplifier also generates a complementary signal, sine omega t, which also multiplies the same output, and is also passed through the same low-pass filter, and this time it picks out the coefficient that multiplies sine omega t in the output of the photodiode, which happens to be simply a sine phi. Okay? Again, there can be a minus or plus in front of it depending on the nature of the lock-in amplifier, but you get these two numbers out of it, okay? So it's simply a multiplication, passing, and then subsequently pass through a low-pass filter. That's what a lock-in amplifier is, okay? And that's how it gets at every point as you're scanning the sample. It's spitting out A and phi at every point. And the feedback controller is looking at the output of the lock-in amplifier and looking to see if this amplitude is equal to the set point amplitude or not. If it's not equal, what is the error? And depending on the error, it moves the Z up and down to keep the amplitude constant, okay? Now, you can actually adjust this cutoff frequency in most commercial AFM systems, okay? In fact, when you talk about lock-in amplifiers, people prefer not to use cutoff frequency, but they tend to talk of something called the time constant of the lock-in, T lock-in, which really is nothing but 1 over the cutoff frequency of the lock-in. That's all it is, okay? So the question is, how do you correctly choose this cutoff frequency or the lock-in time constant of your oscillator? What are the guidelines for choosing this. And often many people don't bother about it, except those who are really high-end users. They understand the compromises involved and they are careful about it. So there are two, I would say, things to be careful about when you choose your lock-in time constant. I encourage you, in fact, to think about, find out on your own AFMs, how would you adjust the lock-in time constant in your AFM? Does it allow you to do it? I guarantee you it does. But you may need to send emails to tech support to find out, okay? But I'm happy to tell you, at least on some of the systems, how to do it. So here are the, I would say, compromises involved. You certainly want the cutoff frequency to be much less than the drive frequency. Why is that? What happens if the cutoff frequency of the lock-in is greater than the drive frequency? What happens then? A lot of noise in the signal. See, remember what you're trying to do is you're looking at the product signal, right? The product signal contains a DC term, it contains 1 omega term, 2 omega term, etc. What we want is the DC term, a nice value for the DC term. However, if your lock-in filter cutoff is greater than even omega, then it's starting to pick out not just the DC term in the product, but also the omega term in the product. It's letting the omega term through in the product, which means the amplitude you would get is really noisy. And you can test this by simply doing an amplitude distance curve. If you do an amplitude distance curve, you expect to see nice, stable oscillation amplitude which decreases, right? What if, as you approach, you see the oscillation, the amplitude really noisy as you approach? That is indicative of the fact that possibly your lock-in cutoff frequency is set too high. As you reduce it, you actually make your amplitude signal much cleaner. It's a very important very important thing to keep in mind. So you want to reduce the cutoff frequency, which is equivalent to increasing the lock-in time constant to get a nice clean value of amplitude with less noise. On the other hand, as you make the lock-in time constant greater, it takes longer to filter the signal. So you got to scan much slower as well. Okay, so this is the trade-off that you have to worry about and decide when you take an image. Okay, the lock-in amplifier. So the whole feedback control apparatus of an AFM consists of the following setup. You have a drive signal on the top left, which is shaking the piezo. The cantilever is oscillating at cosine omega t, but it also has a DC component, it also has 2 omega, it also has noise, all kinds of things in it. You take the deflection signal, multiply it by sine and cosine, pass them to the low-pass filter, as I talked to you about. You generate a cosine phi, a sine phi, and you have little modules that convert this into the actual amplitude and the actual phase out of this, which is why some AFM systems, depending on how they do arctangent, give you either phase lag or phase lead. This is the problem. Okay? And then, as the amplitude comes out, it is compared with the set point amplitude that you set for the image, right? It looks at the difference between the actual amplitude being measured at that point in the sample and the desired set point amplitude. Any difference, delta A, is the error signal that feeds into this controller, which has Kp and Ki, which then changes Z and keeps checking to make sure the error signal goes to 0, basically. It moves Z so as to keep the error signal 0. Okay? This is the basic overall arrangement of the feedback control in AFM, tapping mode AFM. Okay? So let's talk a little bit, try to give you a brief idea of what does Kp and Ki do. So on the top right, you see the general expression for how the Z piezo moves in response to an error signal ET. First term is proportional, and it's trying to push the Z piezo to move proportional to the error signal. The greater the error signal, the more rapidly the Z piezo is going to, the faster the Z piezo is going to move or going to respond. Okay, see what I'm saying? The second term, what it does is it looks at the accumulated error signal in the last let's say time constant of the lock-in amplifier. What's the error signal in that, and then it actuates accordingly. So here's what's going to happen. You have this, on the left of the scan, you've got this amplitude equals set point amplitude, right? Everything is stable. You're scanning a surface, and the error signal will be 0, right? Because the amplitude is equal to the set point. So the error signal is 0. However, as soon as you hit this edge, what's going to happen is the amplitude is going to suddenly change because there's less room for the cantilever to vibrate. Suddenly there's less room, so the amplitude changes. As soon as the amplitude changes, it's different from the set point amplitude. So the error signal changes green at the edge. The controller moves up and down to try and keep the amplitude constant. During the transition process, you see this non-zero error signal at the edge of this object, after which it stabilizes and everything is okay. Okay? That's the basic idea. So the question is, how do we decide Kp, Ki? And by the way, every AFM system has a completely different scale for Kp, Ki. So if you do VEDA simulations of this and you get a Kp value of 0.1, that's not the number that you'll be putting in your AFM system. There's no one-to-one relation between these things, okay? So what are things to keep in mind? Kp, what it does is that, so here's an example of a simple second-order system. This is not the same as our AFM system, but just for a second-order oscillator-like system, when you have a step input, how does the presence of a proportional controller follow the blue curve? If you ask the question, what ends up happening is, as you start increasing the proportional gain, what ends up happening is you start approaching this faster, but if you try to increase proportional gain too fast, you're overshooting. You start self-oscillating. So what ends up happening is if the proportional gain is too high, the Z piezo responds too fast. It shoots over what's required to keep the amplitude constant. And then it realizes, so let's say you're tapping, you're approaching an object, amplitude suddenly decreases, and suppose the Z piezo overreacts because of the proportional gain and moves way up, right? And therefore, amplitude becomes very large again, right? Above the set point. And then the Z piezo says, oh, I've gone too large, and it reacts too fast to come closer. So you have the Z piezo going up and down, oscillating, always overreacting, right? So we don't want too high a proportional gain. And in fact, there's a critical value of proportional gain at which you become unstable. And in AFM systems, you can actually hear that instability when you image. If your proportional gains are set too high, you hear sometimes, at least I think, I can hear a noise. And the reason you can hear the noise is because this up and down motion, unstable motion, happens at a low enough frequency that you can hear it. Okay? It's really interesting, and you change the proportional gain back to 0, and the noise goes away. I don't know if you've had this experience, but it's not, the noise you hear is not the noise of the cantilever oscillating, for sure, because that's happening at very high frequencies. If you hear a noise, it's got to be a low frequency thing. The only thing, sustained oscillation you get at low frequencies due to the instability of the PI controller. Okay? The other thing that the proportional gain you have to be careful about quite a lot is the fact that, as the error signal becomes small, the amount of Z motion starts becoming small also, right? It's linearly proportional. So that sometimes is a problem because it doesn't settle very easily to a steady state value, right? Whereas if you include the integral control system, it's looking at the history of error. And if there's accumulated error, regardless of the fact that the error is very small right now, it's providing a good motion of Z, saying, it's still providing a good number for Z to move, right? So the integral control is good in that sense, and proportional gain alone is not going to be good, In fact, many AFM systems, you can do just fine with integral control. You don't need proportional control. Okay? Main reason is, while proportional control combined with integral improve things, but if you do too much proportional, you get this instability, so there's a problem. Okay? So here's an example, and the next class you're going to do VEDA simulations, and I encourage you for the Tuesday class to bring your laptops. It's going to be a VEDA of scanning now, and you're going to learn about how you create a surface in VEDA, give properties to it, approach a sample, scan, change. You can literally scan in VEDA. It's really nice. And see how these properties influence the image. Okay, so this is an example. I just want to show you. In this particular example, the integral controller is kept at 0, and it's only proportional controller. Okay, and so what you see on the top is in red in the background is the actual height of an image of a feature that you want to image. Okay, so it's a step. That's the red. That's the actual height. It's a 10 nanometer height trench. Okay, I think the free amplitude, I believe, is around 10-20 nanometers also. Okay, so what you see, red is what you want. That's the image you want to get. Blue is the topography that you actually get in an AFM image. So you can see that the image, topography image you get in an AFM is not the same as the real topography of the object. Okay? Why? Because as you hit the edge, the amplitude changes, the Z controller is trying to move up and down to keep the amplitude constant. The topography that is rendered in the image is the motion of the Z up and down to keep the amplitude constant. And so there's transients, the Z is moving up and down to try and get a steady state amplitude. All that transient motion comes into a topography. And so you would see the topography on the left-hand side is like you see higher heights on the when you approach a sample, so to speak. Okay? The different curves correspond to different amounts of proportional gain. The very top solid line, blue line, corresponds to the smallest proportional gain. As you start cranking up proportional gain, you can see that the overshoot you're getting is starting to decrease. What I haven't shown here is that at the smallest, at the highest value of proportional gain here, which leads to very small overshoot, if I crank up the proportional gain just a little bit more beyond that, you get unstable motion. It just goes crazy. So if you do that, then the Z topography of the top actually appears pockmarked because it's going up and down, up and down. It's basically become unstable, the controller. It just goes up and down, and even the top of the topography is not flat. It's like this because the Z is just hunting up and down because it's overreacting to changes. So really neat. So if you went just a little above, you'd get this instability. This is an example you're going to work out on Tuesday in the class. Okay. So one other important thing I want to bring to your attention is, in the AFM controls literature, people talk about climbing up a feature and parachuting off a feature. So you see here that we changed the proportional gain, but the parachuting off is not very affected for some reason. It's not being affected too much by the choice of proportional gain. You see that? Whereas the climbing up is being affected a lot, the parachuting off is not being affected a lot. So the question is why? Why does that happen? That's an important point. Okay? So I'll address that in this slide and bring to your attention two important problems that you need to be aware of when you choose your proportional and integral gain. Okay? One extremely important problem is that of error saturation of error signal during parachuting off. Okay? What this means is the following. We would like for the error signal to increase linearly depending on how far you're from the sample, correct? So, if I hit an object and for whatever reason my Z piezo is withdrawn quite a lot, if I'm very far from the surface, I want the error signal to be large also, so that the controller can then act on it and bring it close, right? But as you can see, we have a bit of a problem. So if you choose, this is the amplitude versus Z for a particular sample. What if you choose a set point in green? Let's say set point amplitude in green. And let's say you're parachuting off a surface. If you parachute off a surface, you're here tapping on the surface. Suddenly you have a chasm, right? So suddenly you're flying high above a surface. So what happened to Z? Z is measured, remember, from the sample surface. So suddenly when you've gone over, Z has become very large. Okay? Effectively. And so Z may have effectively gone all the way to the right, which means the error, what we want though is the error signal should correspondingly increase also, but the error signal saturates. You see, because the amplitude is not, once you lose contact, the amplitude doesn't increase anymore. It remains, it saturates. So my point is that the system is incapable of realizing how far it is from the surface when it parachutes off. Right? When it parachutes off, it doesn't, we want a situation where the error signal is proportional to how far off you are, right? So it pushes down. Now, it will react the same way regardless of if you're jumping onto a very shallow thing or jumping onto a very deep thing. It doesn't realize because the error saturates. You know, beyond a certain height of the object, it doesn't know if it's further or lesser. And so it'll have a certain error signal and it moves accordingly. Whereas what we want to happen is, if it's really far off from the surface, we want it to move faster, move closer, right? This is the problem in the parachuting, is this error saturation, okay? So, error saturation occurs in the following situation. Or how do you avoid error saturation? What you want to do is to be in a situation where the free amplitude A0 needs to be larger than the height of the feature you're trying to image. If you're worried about this parachuting effect, this tail effect. Why? So again, the statement is, if you want to be sure of that, you want to make sure your free amplitude is larger than the height of the object. Okay? Or actually, to be more specific, what you want is, let me go back and clarify that. What you want is, so you've got a step, you're coming off, you're oscillating with a set point amplitude A. When you come off, you still want to be tapping on a sample. You don't want to lose contact with the sample. So, if ideally when you come off and, you know, the amplitude, you know, you got more room to vibrate, so its amplitude starts increasing, right? If the free amplitude is large enough that when you come off the edge, it still taps on the sample, then you're okay. On the other hand, if your free amplitude is small enough that when you come off the edge, you know, when you come off the edge, the amplitude increases, but it's not tapping anymore, then you're in problem, okay? So what you want to make sure is when you come off the edge, the free amplitude that you have is large enough that you're still touching the surface. That's what you want to make. So one common strategy for reducing the parachuting effects is to crank up the oscillation amplitude, reduce the set point, so that when you jump off, you're still with large enough oscillation that you're tapping always in the surface. If you lose contact, then you're in trouble. That's where you get saturation error, error signal saturation, okay? This is a very important thing. Usually is not important when you're imaging things like nanoparticles, but when you're imaging slightly high things that are more than 10, 20 nanometers, you need to worry about it. The second important thing that we have actually discussed in the past is, you know that as you approach a sample with Z, you get this jump from attractive to repulsive, right? And sometimes you get two values of Z that give you the same amplitude. And you can imagine, how is the control system going to react to that? The control system is trying to get the error to 0, right? Error is defined as amplitude, measured amplitude minus set point amplitude, right? But when you're choosing a set point where you have two possible amplitudes for the same Z, the controller can push you towards either one state or the other state. It doesn't know the difference. It's just trying to get the error signal 0, and the error signal will be 0 in both cases, okay? In both amplitude values. So you can have these situations where you're scanning a sample and sometimes you're in the attractive, sometimes in the repulsive regime. Both give you the same amplitude, and the controller thinks it's doing a great job keeping the error signal 0, which it is, but it's shifting back and forth between these two states, creating artifacts in the imaging. So that's another thing you need to be careful about, okay? So that's all I've got for today. And next class, please bring in your laptops. We're going to be doing scanning using VEDA tapping mode and studying how to play around with KP and KI in the class, okay? Great.